let's just think back to where we began, right? We said this topic is called trigonometry, right? Which is just about measuring triangles. That's what the name means, okay? But very, very quickly, we moved from trigonometry to a very specific part of trigonometry, namely all this sine, cos, tan business, right? Now, these are not trigonometry, they're just one part of it. They are the trigonometric ratios. And we went over this in our first trig lesson. We said SOHCAHTOA, opposite, hypotenuse, adjacent, all the different combinations of those give you ratios, and we give them names, and that's where we started, okay? But you quickly realize that this is a very limited way to define these things, and therefore this, right? Because have a look. Here's a typical right-angled triangle, right? And if you wanted to work out what sine of theta or cos of theta or tan of theta and all of the reciprocals are, you're kind of limited, right? So you've got your opposite, your hypotenuse, and your adjacent here, right? So you can get different ratios, but theta, and we noticed this in our proof by contradiction about the tangent being perpendicular to the radius, we noticed that theta automatically is locked into a certain domain. There are restrictions on theta. What are the restrictions?
0 and it's in between 0 and...
Good. So yeah, theta's acute, basically, right? This is a problem because if we want to understand angles, right, you don't even have to leave triangles. If I just push this triangle over to the side, right, like so, okay, like there's an angle over here. Let's call that alpha. Can I do trig with that angle?
Yes.
Like, if I look at this, I can't because it's not acute anymore, right? So here, my definitions, my very, very narrow definitions of the trig ratios, they immediately break down, right? And then what about trig when the angle's not in a triangle, right? Where's the opposite in the hypotenuse? There's no hypotenuse. What do I even do, okay? So this is a nice way to start. Right-angled triangles are a good beginning, right? Because they're understandable. But they're no good, right? When you think about obtuse angles, or reflex angles, or bigger angles, or what about just boundary angles? What about 90? Oops, right, I have a 90 degree there. What's sine or cos of tan of 90? How do I work out what these are? This definition isn't going to fly, okay? And that's why what we're going to do is we're going to take this definition and we want to understand not just ratios, we want to move toward trigonometric functions. I want you to think back to the first time you heard the word function, right? What is a function? What's a function?
F of x.
We tend to write it with the abbreviation f of x, right? A function is just something you can stick a number in and get a number out. Excuse me. Thank you. Okay. Simple concept. Stick a number in, we call it x. And out will come another number, and we call that f of x, right? And we know all kinds of functions already. 2x, 3x minus 1, x squared, log of x, blah, 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 okay? So what we want is, can we define sine or cos and tan in a way such that I can put any x you like, right? Not just within this little spot. Such that I can get a value out the other end. I want to generalize. I want to blow open my world and not be stuck in right-angled triangles anymore. Okay? So the way we're going to do this is with a circle. Not just any circle. This is the unit circle. Okay? So it has a radius of 1. Right? There's a radius of 1. Now, the unit circle is inextricably tied to the trig ratios and the trig functions. We shouldn't be that surprised because as we were just explaining, you know, even one of the basic functions, namely tan, is named after a component of a circle, right? So we should expect that there's some kind of link here. In fact, in some of the older textbooks that you'll have a look at, when they're looking at trigonometric functions, the chapter isn't even called trigonometric functions. It's called circular functions. Sine, cos, tan. That's what they're called, right? So fundamental is the circle to understanding these, okay? So here's the way we're going to go through this. Here's your unit circle, and we're going to put one of these right-angled triangles in our circle, okay? So I'm going to put it right here in the same orientation as my That's not very, well, it'll do, okay? As my triangle over here, okay? So, there we go. Now, I put it here, and so I'm going to put my theta in the same spot as well. So I actually have a full triangle here. Now, before I go any further, I want to immediately draw your attention to the fact that, why do I start here? I start here very on purpose, okay? And it seems a bit confusing because we have measured angles around a cross-looking thing before when we did bearings. Remember that? Okay, bearings, we've looked at this. But this is a bit weird. Let me show you. When we do bearings, we know how to do north, south, east, west, etc. Okay? But true bearings, which are measured all the way around, where did true bearings begin on a diagram? North, east, west. Where do they start? They start at north, right? True north, okay? And then we measure in which direction? We go clockwise, okay? Right? And this kind of makes sense, I suppose, for bearings, because north is a sensible place to begin, right? North's like your most important direction. And clockwise, well, it's clockwise because that's the way our clocks go, right? So why not measure that way? Okay, when we're in the unit circle and when we're in trigonometry, okay, things are completely different. So number one, north is not the starting point. Okay? Instead of north being the starting point, on here, it's east, it's the x-axis. That's our starting point, okay? Not only is that different, this is different too. We don't measure clockwise, we measure anti-clockwise. Now, just before I give a bit of an explanation, I want you to have a think. Why do they do this, right? Why do they make them different? We're both trying to understand the same thing, angles, okay? Why on earth would they not only change the starting point, but the direction? As we go through this, I wonder if you will start to see why this absolutely makes sense in this context. In fact, if anything, the bearings are the ones which are a bit sort of arbitrary. Why start with north, okay? So that's an important note, and that's why I'm starting here on the x-axis, and my angle theta is measured anti-clockwise. You see that? So I'm going around the circle this way. Okay, now, what I want to have a look at is this right angle triangle here, okay? And just like in our very first question this morning, which is why I started with it, right? These sides here, I can phrase in terms of the trig ratios, okay? Now, if I say, okay, I've got a point up here on the circumference of the unit circle, okay? I want to know what its coordinates are. Well, its coordinates come from what's its x value, horizontal, and what's its y value, vertical, okay? Don't forget, it's the unit circle, so what's the hypotenuse equal to? 1. Okay, so down here, here's my x value. X equals, now what is x equal to, right? Well, I've got this side down here, and I know what the hypotenuse is. So being that this is theta, which trig ratio should I choose which will relate those two sides? It's cosine, isn't it? Because I've got adjacent and I've got hypotenuse. In fact, you can just quickly mentally do it. Cos of theta will be adjacent on hypotenuse. X on 1, it's just x, right? So x is just cos of theta. That's what it's equal to, okay? In exactly the same way, when I look at y, I've got the opposite side this time. So sine of theta would be opposite on hypotenuse, it's just y. So y is equal to sine theta. So now I'm going to stop talking about x and y for a second because I can just talk in terms of theta, right? So when I name these coordinates up here, the coordinates of this spot are cos theta, sine theta, whatever theta may be. Okay. So what have we done? We have taken this idea here about right angled triangles, right? And we've applied it to the circle, and then we've noted this interesting relationship. That cos is the x coordinate of the point on the unit circle corresponding to this angle. Let me say that again. The cosine of theta is the x coordinate of the point on the unit circle that corresponds to that angle, right? And the sine of theta is the y value, right? So I'm now going to change gears. This is weird. I am just going to stop defining sine and cos in terms of this triangle. I'm now going to define sine and cos in terms of this circle, okay? Like in fact, I'll just go over here. If I drew a new unit circle, right? And I put like a dot over there, okay? I can define that point as cos theta, sine theta, no triangles involved if measuring this angle around, that's theta. Do you see? This is a really big deal, right? Because, and this is why they're called circular functions, right? There are no triangles here. At least no triangles that I need to draw, right? Cos theta and sine theta simply come from where am I on the circumference according to what angle you've given me, okay? Does that make sense? Now, as you'll see in the next 5 minutes, this definition is so much better than our old definition. It's far more powerful, it's far broader, and it yields a lot of insights, okay? So, just before I leave this, okay, what's tan? What's tan?
Sine or cos.
It's just the ratio between the y and x coordinates, isn't it? Okay?